So let's just review the learning guide on transformations. I've got a function up here, y equals f of x. And here's my new function, y equals 2f of 3x minus 2 plus 4. So just to refresh your memory, the 2 in front of here would be a vertical expansion by a factor of 2. The 3 in front of the x, the coefficient of x, this makes a horizontal compression by 1/3. Then we would move right 2, and replace x with x minus 2, right 2, and up 4. So what we're going to do now is we're going to take our basic 6 graphs that we worked with before, and we are going to apply transformations to those functions. And so, assuming you reviewed your transformations, if we had the graph of y equals sine x, we should now be expected to graph functions like this. And this function here would simply be the same one as this graph, except you will need to vertically expand it by a factor of 2. You would need to horizontally compress it by 1/3. You would need to then move it right 2 and move it up 1. So let's look at how we would graph some of these. We'll start with a much simpler example. Let's say we were asked to graph y equals 2 sine x minus 1. Well, we recognize that the original graph is the graph y equals sine x. I'm just going to plot the basic graph here, the y equals sine x graph. Okay, so there's the graph of y equals sine x. That's the one in blue. We have two transformations here. We have a vertical expansion by a factor of 2, followed by a vertical translation down 1. So let's vertically expand this by a factor of 2. Well, 0 times 2 is still 0. 1 times 2 is 2. 0 times 2 is 0. Minus 1 times 2 is minus 2. And 0 times 2 is still 0. So this function here would be a vertical expansion by a factor of 2. And now I need to take each of these points and move them down 1. Oh, we're going to need to go down to minus 3 here. All right. Now let's erase these other ones. Okay, so here is a graph. Here's a graph of y equals 2 sine x minus 1. Just going to point out a couple of things here. And that is, first of all, this number here, this vertical translation, this minus 1. This number here, we're going to have a new name. And we're going to call this the vertical displacement. Okay, so just a fancy name for our translation, our vertical translation at the end. We're going to call this the vertical displacement. That means that this graph is simply moved down 1. Now, if we look at this line, minus 1, see how this line becomes sort of the center of our graph? It's centered at minus 1, and it goes up and down from that line. So you can think of the vertical displacement as being think of it as the center line of your graph. Okay, think of it as your center line of your graph. The graph needs to be centered at minus 1. This number here is what we are going to call the amplitude of this function. And the amplitude is simply the distance, call this A for amplitude. The amplitude is the distance from the center of the graph to its maximum point. Distance from center to the maximum. The distance from the center to the maximum is defined to be the amplitude of this function. So we would say that this graph here has a vertical displacement of -1 and the amplitude of it is 2. Let's look at another example. Say we were asked to graph this function here. Well, I know the amplitude is going to be 3. So in other words, the distance from the center to the top of this graph is going to be 3. I've got x minus pi over 2. That means it's going to go right pi over 2 and then up 2. The vertical displacement is +2. The vertical displacement up 2. So if I were to graph this function, let's start with a basic cosine graph. By now you should be good at drawing the basic cosine graph. Alright, so there it is here. This thing needs to have an amplitude of 3, so we will make this have an amplitude of 3, vertically expand by a factor of 3, gives us this graph. So here's a cosine graph with an amplitude of 3. Then we need to take this and move it right pi over 2 and move it up 2. So I'm going to do both these steps at once. That means I need to move each of these key points. I need to move them right 1 square, because each one of my squares is here. Each one of my grids is pi over 2. So move it right 1 square and move it up 2. So this point, if I moved it right pi over 2 and moved it up 2, would appear right here. This point, if I moved it to the right pi over 2 and moved it up 2, would be here. This point, moved right pi over 2 and moved up 2, is right here. Right pi over 2 and moved up 2, right here. And this point moved right pi over 2 and moved up 2 is up here. And so let's see, do we have a cosine graph? Of course, this is going to carry on. We could draw more cycles there. Do we have a cosine graph that is centered at 2? There's the 2 line. Yes, this graph seems to be centered at 2. Does it have an amplitude of 3? Yes, from 2 up to 5, there's an amplitude of 3. And is it moved, here's our key point up here, is it moved right pi over 2 and up 2? Yes. We have a center here of 2, and it's moved right pi over 2. So once you've drawn it, it's very easy to check. Do we have a vertical displacement of 2? Yes. Do we have an amplitude of 3? Yes. And is this graph moved right pi over 2? Yes. It starts at pi over 2 as a cosine graph. I've got a picture here of the graph of y equals sine x. Here it is right here. You're familiar with that. Now let's see what happens if we replace x with 2x. Well, we know that should be a horizontal compression by a factor of 1/2. So that means that instead of taking 2 pi to do 1 period, this point should be compressed by 1/2. And so this point will be pi over 2, and this point pi over 4, and this point will be 3 pi over 4. So we define a function's period to be the length, talking about a function's period, the period is the length it takes to do 1 cycle. So here, the period of sine x is normally 2 pi. It takes 2 pi units to do 1 of its cycles, and then it continues on again. What we've just done here is we have compressed this graph by a factor of 1/2. so its period is now pi. So this gives us a new formula. The period of a function will be equal to 2 pi, because that's normally the period of this sine function, 2 pi divided by the coefficient of x. So what would be the period of y equals sine 3x? Well, the period would be 2 pi divided by 3. In other words, if we were to sketch this function, this point right here would be 2 pi divided by 3, because its period has been compressed by 1/3. So instead of 2 pi, it's 2 pi over 3. So if we consider the function y equals 2 sine 3x minus pi plus 1, we should be able to list all of its properties: its amplitude, its period, its phase shift. And phase shift is simply the word that we give to the horizontal translation, and its vertical displacement. So very quickly we can look at this function and say this graph needs to have an amplitude of 2. This function needs to have a period of 2 pi over 3, 2 pi divided by the coefficient of x. Its phase shift is it's been moved right pi, x minus pi moved right pi, so phase shift right pi, and the vertical displacement is up 1. So if we started with a basic sine graph, which we know looks like this, we just have to change it to make sure that it has an amplitude of 2. So the distance from here to here instead of 1 needs to be 2. It needs to be centered, the vertical displacement, it needs to be centered at this line right here. And then it needs to make sure that you have a period of 2 pi over 3 and a phase shift of right pi. So let's see if we can sketch this one then.
Before we look at that example, let's review some of the properties of trig functions, and you can make sure you have these notes in your journal. So if we consider y equals a sine of b x minus c plus d, then the amplitude will be a. That's the distance from the center line to the maximum value of the function. The period will be 2 pi divided by b. The period is the length it takes to complete one cycle. The phase shift would be right c. Phase shift is the translation left or right. And the vertical displacement would be up d. The vertical displacement will be the center line of the graph.
So here's that function, y equals 2 sine 3 x minus pi plus 1. I've written down the amplitude's 2, the period's 2 pi over 3, the phase shift is right pi, and the vertical displacement is up 1. You might want to split this up into two or three different graphs until you've got what you want. I know that this needs to have a vertical displacement of 1. So my center line has to be at 1. And I need to have a sine graph with an amplitude of 2. So if I started here, I would need to have a sine graph going up 2 and down 2. And notice I've got to have a period of 2 pi over 3. So I've made my scale here in pi over 3s. And if I've got to have a period of 2 pi over 3, that means I've got to end once more right there. I've got to end at 2 pi over 3. Well, if I've got to have an amplitude of 2, then I better be going up 2, down 2, and back up to the y equals 1 line. So I now have a sine graph. This looks like a sine graph. It has an amplitude of 2. The distance from here to here is 2. It has a period of 2 pi over 3. You can see that. Its period is 2 pi over 3. It has a vertical displacement of 1, meaning it's centered at the line y equals 1. I just haven't done the phase shift yet, which was to move at right pi. So I'm going to do that right now, which means this point has to be moved to the right pi. Well, that's 1, 2, 3 on my axes here. So this point I move to here. This point I move 3 spaces. Actually, what I'm going to do is I'm going to move this one 3 spaces. So 1, 2, 3. And this one 3 spaces. 1, 2, 3. And then halfway between here and here, I need to be up at 3. Halfway between here and here, I need to be down at -1. So erasing this one. Okay, I now have one cycle graphed here. The nice thing about graphing these is you can always verify that you've done it correctly at the end. Do we have an amplitude of 2? Yes. Distance from center to top is 2. Is the center line at 1? Yes, the center of this graph is at 1. Does it have a period of 2 pi over 3? Well, 5 pi over 3 minus pi, if you subtracted these, 5 pi over 3 minus 3 pi over 3 is 2 pi over 3. So yes, that distance is 2 pi over 3. And is this a sine graph that's been moved to the right pi? Yes, it's a sine graph that starts at pi. So we have correctly graphed one cycle of this function. And we could simply continue this pattern if we continued with these points. So now I've got 2 cycles drawn here. We can continue those points to the left and to the right if we desire. So that's how we graph trig functions. We could do the same thing with cosine, same thing with tan. We would then simply need to do the transformations of those functions. So what I would encourage you to do is when you're given the equation that you're asked to graph, write down what's its amplitude, period, phase shift, vertical displacement. Start with the basic graph and then do your transformations one at a time or 2 at a time, whatever you feel comfortable doing, until you get all 4, in this case, all 4 transformations done. And just before I move on to the next expectation, I want to remind you that we could also have negative coefficient. And if you remember, if you have y equals f of x and y equals negative f of x, a negative in front is a reflection. Remember? Reflect in the x-axis. So a cosine graph, which normally would look like this, if we were graphing y equals negative cosine x, okay, so there's cosine x. Graphing negative cosine x would simply be reflect the points in the x-axis. And erasing the original function, I now have a picture of what y equals negative cosine x looks like. Let's see if we can list the properties of this cosine function and what transformations have been made. Amplitude of this function, now the coefficient is -3, but the amplitude is still 3 because all this negative is going to do is reflect it in the x-axis. It'll still go up and down 3 from the center line. So the amplitude is 3. There's just been a reflection in the x-axis. The period, now here's an interesting thing. Remember we said the period is 2 pi divided by k, where k is this number in front of x. So here, it'll be 2 pi divided by this coefficient of x, which is 2 pi over 5. So if we have 2 pi divided by 2 pi over 5, remember anytime you're dividing by a fraction, it's the same thing as multiplying by its reciprocal. So if I flip the denominator, it's 2 pi times 5 over 2 pi, and these conveniently cancel out. So the period of this function is 5. It's going to take 5 units to do one cycle. Then the rest, phase shift would be left, pi over 3, and the vertical displacement would be -4, or down 4. So this is kind of handy. If you happen to have a 2 pi in front of x, then the period of this function simply becomes the denominator of this coefficient. 2 pi divided by 2 pi over 5, 2 pi's cancel out, and we just have simply a period of 5. So that's good to know too, because that works well in the applications that we're going to look at next.